Hey guys, my name is Theoletta Kobe and I am a junior here at Washington and Lee, and I'm about to give the presentation on the equation of a straight line. Thank you for it. You had to formulate an equation for these set of points. What would you do? Connect every dot together until you had some crazy roller coaster looking thing? Or would you use a quadratic function or maybe even a cubic? But maybe those might not fit right. There's a better way. You can use the equation of a straight line. The equation of a straight line describes a relationship between two variables and provides a fit for various sets of data. So why use the equation of a straight line? Many relationships in chemistry can be expressed in this form of straight lines, such as rate equations or the absorbance of light. Maybe you don't believe me, but I'll show that it's true in a second. Most of you might be more familiar with the straight line equation of y equals mx plus b. It's a pretty common way of writing it, and all of these equations below it can be expressed in the same way. The equation of a straight line ensures a fit for any set of data points that can be repeated by others. It can also make sure that the trend is visible, whether it's a decreasing or increasing trend. It will be clearly visible to anybody who looks at the line. So let's first look at the rates of a reaction first order equation. So for this equation, we're going to use X to represent the concentration of a species A. So most of you may remember this as being a bracket symbol around the A, but just to make it easy for us, I'm using X to represent that. Next, we have initial concentration, which is where time, which is another variable of this equation, will be 0, and this will have a value of its own. Then we have K, which is slope or rate constant. To express this equation, it is a measure of the concentration A at a specific time interval. All right, let's start breaking it down a little bit. First, if you take the natural log of this equation, you'll see that you need to know some tricks back when you learned natural log in high school. First of all, those that are multiplied within the same natural log can be separated into this addition format. Then we also have anything raised to the power within a natural log can be placed in front and multiplied by the natural log instead of trying to do this crazy math. Also, we're lucky. ln of e will always equal 1. So what we're left with is negative kt. And then we're left in this form, which some of you may have recognized right away, that it is y equals mx plus b. And just in case you don't remember y equals mx plus b, ln of x for this equation is the dependent variable, or what you'll find on the vertical axis. Negative k is our slope. Our independent variable, or horizontal axis, will be t, and our y-intercept, where x equals 0, is ln of x naught. So here's a little information you need to know before we get into the practice problems. 0, first, and second order are all types of orders that will be discussed in a later video. But for this video, you need to know that they all have independent integrated rate equations. And they also have different points where they will show a straight line. You'll understand this a little bit more when I get into the first problem. But when you see x versus t, that will be 0 order, while ln of x versus t will be first order if you see a straight line there. All right, let's get into the first. So example 1, the data for the decomposition of dinitrogen monoxide, aka nitrous oxide, is in the table next to us on a given surface at 900 degrees Celsius. Verify that the reaction is first order by preparing an ln of x versus time graph, and then determine the decomposition rates at 900 degrees Celsius using the straight line equation and K. So let's go over to the Excel file. So first things first, we know this equation has to be in first order. So we have to take the data that they have given us and take the ln of each concentration. So an easy way to do this is to type equal ln of x, and then ln, and then the number that you want to use for it, then click the exact box that has that number. And then voila, it gives you the ln of the concentration that we're looking for. And then if we drag this little part down, it will repeat the same function for the next numbers to this side. So then we just go ahead and graph this data here. Go to insert, go to scatter plot, because what you don't want to do is accidentally click line graph, because we don't want it to look like some crazy connect the dot looking thing, because it may not be accurate representation. So after this, there we've gone. Graph the data that has been given to us, ln of x, Then we click the plus sign to the side, click this arrow here, click more options, make sure it's on linear because the other ones may not fit exactly. Like power they've already gone ahead and taken out power and exponential because it won't work for the data that has been given to the system. Then you click display equation on chart, and there it is, the straight line equation for these data points. And wonderfully so, it's almost touched every point on this line and it's showing a straight line. So the answer you'd give back to your professor or anybody who asks would be this, that table right here. Perfect. All right, now we have this second example. The decomposition of HAOF occurs at 25 degrees Celsius. So using this data in this table, we need to determine the straight line equation and calculate the slope. Let's go over to the Excel. I hope you were able to take a moment to copy down the data that we're about to use. So this one's a little bit more complicated because they didn't specify whether it was first order, second order, or zero order. We have to do a little bit more thinking. So first let's test out whether it's zero order, which in this table right here has to be X versus time. All right, so X versus time, then we go insert again and scatter plot, and then graph trend line. So this one, it's a little bit off. This one's not exactly on the line. All right, let's do second order, in first order, sorry. And then close it up, and then drag and drop once again. And we graph this by highlighting the data that we'd like. Oops, let's not have that happen. Control, highlight, insert, scatter, and then add the trend line, the linear. Oh, this one's perfect. But just to make sure that this is the right order, we go ahead and click equal once again, and do 1 over X, oops, which is going to be this variable, close it up, then drag and drop so it copies the same function, and highlight this one, and highlight this one. Oh, make sure not to grab any extra boxes. Any extra boxes could cause Excel to freak out. So here we go, and we add in a trend line, and see, this one's not right either. So obviously, this is another first order reaction. And we can use this one to get our straight line equation. So we go back and click here, click display equation on the chart, and that is what you turn into your professor if they ask for it. There's just a few things that I'd like to recap for you guys before we go. So the reason why you need to understand the equation of a straight line is that it appears in several concepts in chemistry and mathematics. The equation of a straight line is also used to provide a fit for a specific set of data points. Using an equation of a straight line can ensure that your data other scientists can see the same fit that you've seen within your data. So first order rate of reactions equation from kinetics is a straight line equation and can be rewritten as such using natural log. Understanding how to use Excel to graph data points and determine the straight line equation is an important concept, especially to save you time in lab, lecture, and possibly your future career. Thank you for listening to my presentation.